and so there is no one in the class, but there are, but I'm still here, yes. So please be more active with questions, yes, because of this. So, and please also let me know, because part of the class I would speak with Blackboard, yes, because there would be kind of exercise style slides. Then please, if you don't see very good, on what is written on Blackboard, just let me know. Okay, so short summary of what had happened in the previous class. So we introduced notion of mixed states, yes, which was that we do not have a state with an exact value, yes, but we have some probability we are in a state, so with probability pk in a state psi k. We introduced notion of density operator, which represent this mixed state. And we show that actually if two mixed states have the same density operator, then they are indistinguishable. So there is no way that we do some quantum operations, measurements, that we can say in which of those two states we are. So kind of the density operator fully describes what is happening in the system. Yes, and we realized, we saw how it works, what means apply gate to it. Yes, it is a conjugacy by operator. And we realized that measurement actually acts also in the terms of density operators. Yes, so philosophically, I made a statement that all the previous 10 lectures which I gave, I can give not in the form of vectors in complex space, but in terms of density operators, yes. But of course, the language of states, which are vectors in a complex space, is easier. Yes, and most of algorithms works there. And I want to use density operators in order to work with the noise, yes, so with errors in quantum systems. Yes, because if we have errors, we cannot stay in the language of states, psi k, yes, because error happens with a probability. It's not necessary, yes. So usually with a small probabilities, you have a noise state, and with larger probability, and with other you have the kind of the not noise, so the one which was corresponding to first 10 lectures. Let us understand deeper what is going on here, and let us explain how we would describe noise. Yes, what are the limitations? What could be noise, and how it can act in a space of mixed states. So what is possible there? Yes, because we remember that for classical, for just poor quantum states, we were able to use unitary operators, so we had certain restrictions. So what are restrictions for the noise? Yes, so what can look like a noise? Yeah, so for this, we will need to do a bit more notation, and this a bit more notation also has a meaning. So I will introduce the reduced density operator, which works as follows. So I feel that we have a lot of qubits, and we separate it into two groups, group A and group B. Yes, I will call them registers. And A would correspond to the part of the system in which we are interested. Yes, I call it quantum system. So our system which we really observe and which we would measure, which we care about. And there is other part, B, yes, which is an environment. Yes, so because in a perfect world, of course, you leave just your system as just your system, but in fact, it always have interactions with the real world around us. And moreover, when you apply gate, it's always happened that, I mean, something comes to your system and apply gate. Yes, so you, in any case, interact with the things which are around, so interact with environment. And first of all, this is a huge source of noise. Yeah, so this is like your spontaneous interactions with environment would be noise generator. And another thing which we do then when we apply operations, we interact with. And now I want to define the notion that even that we know that there is environment in the system, I want to give a formal definition and I want to define what means that if I have a full system AB, what is the state of the first part? What is the state of R, of quantum system by itself? Kind of ignoring the state of the B, of environment. So this is a concept which I would like to introduce. Yes, and this will be called partial trace. I will define on the next slide. Yes, so if we have a quantum system of mixed states on AB, partial trace or reduced density operator would be thus an operator which moves the state of system AB to the state of system A. Yes, it's a reduction of dimension because rho AB acts on a bigger system, so this is an operator, but you should not expect that this is unitary or something like this. Yes, because it acts between different spaces. And so, now the definition. The definition is not very pretty, and it comes from certain principles of quantum mechanics. Yes, but I would not give those principles, I would just give a definition. Yes? So, we have an operator. First of all, it would be a linear operator. And this comes from general paradigm of quantum mechanics that everything is linear. Yes, but once again, it is linear, but it cannot be considered as a unitary operator. Yes. So, and the second thing, I want to define it, how it acts on a tensor products. Yes, so if I consider certain operator which acts on the first part and a certain operator which acts only on part B. So if you have two independent elements, yes, basically, then I define it by exact format. So I will say that the first part, and here I consider not everything. Yes, I consider operator which is generated by two states, A1 and A2, and their outer product. Yes, and B1, B2 also like this. Then I consider the first part I do not change, and the second part I replace the tensor product by the trace of it. So I replace an operator by a number. And we remember, yes, so that in a certain sense, trace of an operator should correspond to the probability of these events happens. Yes. So, and because there was a trace of density operator was 1, so we would expect that it is equal to the probability. But it's not very good analogy because it's not necessarily positive, for example. Yes. it would just give us a good definition. And just to recall, the trace of such outer product is the scalar product of the vectors. So I give this as an axiomatic definition. Yes, and now why it allows us to define the fact that it is linear in this relation, why it allows us to define the density, the reduced density operator for any state. And the reason is very easy, yes, because let us recall how density operator look like. Yes. So we have a huge matrix, yes, where on each row and each column, yes, on each element here, yes, we have that it corresponds to certain basis and so let me write A1, B1, yes, and here there is a vector A2, B2, yes, and then just element which is here, yes, so here is a certain value Z, yes, then it's part of the matrix, so Z, A1, A2, B1, B2, yes, so then the matrix by itself, yes, the density operator is equal to sum over all A1, B1, A2, B2, yes, so Z, A1, B1, B2 times A1, B1, A2, B2. Can you see this on the board?
What is on the far right is a little bit difficult.
It's a little bit difficult, yes, so let us. So where is the line where you can see? Here, can you see?
I can see clearly until the summatory.
Until here.
Yes.
Okay, so then I would erase everything which is, but it's quite strange. Let me see, because I expected that. Okay, I see. This is because of the blinks of light. Yes. Okay, I see. Mm-hmm. Yes. And okay, so then I would use only the part which is the left. Yes, and then what you can say that so the line here is okay. Yes. Question? Yes. Okay. So then the row can be written as the sum over A1, A2, B1, B2. Yeah, so Z, yes, is this index, and times A1, just a second, a row would be sum Z, A1, B1, A2, B2. Yes, but this would be exactly equal to the sum of Z, A1, A2, then Z, B1, B2. Yes, and because by the definition we know what is the trace B, partial trace of this element, yes, so then we can calculate the partial trace of the sum in general. Yes, and on the next slide we will see examples. We will calculate this on certain complete matrices. Yes, and there is a question why it is not self-contradicting. Yeah, because here I didn't ask B1, B2, or A1 to be a basis states. I just solved it for A1 to B1, B2. This equality is correct. Well, I mean, this should be proved, and people prove this, and let us not do this. Let us just rely to this definition. Yes, and what is important is that if you, as a consequence, that if you consider two states which are, if your density operator is just tensor product states A and B, so the A and B are independent, then partial trace would coincide with the density operator of system A. Yes, and you can see this in a certain sense clearly here, yes, because if the rho B is a density operator, then it would be represented in such sum with B1 equal to B2. So, I mean, this is not difficult to see this, yes? And this might be was driven definition. Yes? So, but here it is more general. Yes, so we want to have this property, and we want operators to be linear. Yes, and a good definition for this it happens this one. Yes, let us see how it actually works. Yes, so let us consider poor state psi like this. Yes, which is sum of 0, 0, 1, 1. What is the density operator corresponding to it? Let us do this together. So first of all, yes, how you will start? Yes, let us write a matrix. Yes, density operator is a matrix. Yes, let us start and with what we start. Yes, so the density operator is just psi, psi. Yes, we want to open brackets. Yes, so this will be 1 over 2, 0, 0 plus 1, 1 times 0, 0 plus 1, 1. Yes, what matrix corresponds to it? Yes, so this would be 4 by 4 matrix. Yes, and we write here the states 0, 0, 0, 1, 1, 0, 1, 1, and here 0, 0, 0, 1, 1, 0, 1, 1. Yes, and now we should fill up this elements. So, yes, what would be the coefficients? What would be the value here? In what value corresponds to 0, 0 multiplied by 0, 0?
1.
What?
1.
1. Does there exist other visions? In fact, you were correct, yes, because you have here 0, 0, 0, 0, yes, the product gives 1, but you have 1 half in front. Yes, so you should write here 1 half. Yes, because you have on front multiply. Yes. What would be here? Zero, 0 times 0, 1. Is it in this product if we open?
No, it should be 0.
So it should be 0, 0. What is here? 0, 0 times 1, 1.
0 as well.
No, because if we open the brackets, yes, what we would have? The 1/2 will have 0, 0 times 0, 0 plus 0, 0 times 1, 1 plus 1, 1, 0, 0 plus 1, 1, 1, 1. And so that's, here would be 1/2 as well. Yes, here would be all zeros, here would be all zeros, because we don't have 0, 1 as the first on the cat part. Yes, on the left side of the inner product, we have only 0, 0 or 1, 1. Yes, and those would be 1/2, 1/2 as well. Yes, so this is the matrix. Yes, this is the density operator of such a state. Yes. Let's try to find its trace. Its trace. So first of all, the just trace, yes, the just trace is equal to 1. Yes, so if you look like this, it is 1. And this is what it should be. Yes, because density operators must have the trace equal to 1. Yes, okay. What is for this operator? Yes, I suggest to look onto this representation, not to look on the matrix by itself, but to look on those brackets. Because what we can see here, that each term which is written here have the form from the previous slide. It has this form. Yes, and so because it's linear, so then we have the trace B, yes, trace of the second qubit would be just equal to 1/2 trace B of 0, 0 plus 1/2 trace B of 0, 0, 1, 1, 1, yes, plus 1/2 trace B 1, 1, 0, 0, and plus 1/2 trace B 1, 1, 1, 1. So I just used linearity. Yes, so I can see that, so trace B of psi psi is equal to sum of the 4 terms because of linearity. And I would switch to the black, yes, marker, and let us see what would be here. Yes, I would erase matrix, and let us see what would be the result. Yes, so what is trace B of 0, 0, 0, 0? It is equal to trace B of 0, where is this? Is the first qubit, 0. So I took the first elements from here, tensor, 0, on the second qubit, 0. Yes, I took elements from here. Yes, and it should be equal by definition it should be equal 0, 0 times trace of this one. But I show that this is a scalar product of them. Yes, so. And it might be not the best notation, but the scalar product of two equal vectors, which are denoted 0 here, yes, is always 1. Yes, because this is vectors. So those vectors have lengths 1. Yes. So it is 0, 0. What would be trace B of 0, 0 times 1, 1? Yes, it's applying the same idea. We get 0, 1 tensor, and this is first qubit, tensor 0, 1, and this is second qubit. And so by our definition, it would be 0, 1 times scalar product of 1, 0. And 1 and 0 are two orthogonal vectors. Yeah, so this scalar product is equal to 0. So it's not a vector. Yes, and applying the same ideas to other terms, yes, we will get trace B of 1, 1, 0, 0 is equal to 0, and trace B of 1, 1, 1, 1 is equal to 1, 1. Yes, and so summating those elements, we will get that we will get that. So can you see a bit more here or not really?
I think with the black pencil, we can see it more.
You can see a bit more. Yes, so that's, let me, so remember this one. Up to here you can see.
Yes.
Yes, great. Then we will get the trace B of psi psi would be equal. The first element, so the 1/2, yes, 1/2 0, 0. Sorry, I would erase better. 1/2 0, 0 plus 0 plus 0 plus 1/2 1, 1. Yes, which is, if you look onto the matrix, it is 1/2 0, 0 1/2. And interpretation of it, yes, interpretation is that 1/2 probability that you are in the state 0 and 1/2 probability that you are in a state 1. And this is important kind of philosophical concept that if you consider this state, so you have exact state, you have poor state, but there is an environment, so there is a second part of it somewhere. Yeah, so we have two parts. And kind of, if you detach, yes, the the idea of partial trace is the same as you ignore the second part. And it is the same as you detach it, kind of. You remove it out of your system. At that moment, it says, okay, I'm not now a poor state. I kind of become with probability 1/2 0 and with probability 1/2 1. Actually, detaching of the system, yes, I don't know why I didn't try it on the previous slide this, detaching of the system is the same as measuring B, so trace B is the same as measuring B and ignoring its the result of measurement. Yeah, so kind of if we don't know, if we say that we never read them, we do measurement but never read the value. Yeah, so in that case, the systems, this is what is happening with A. Yes, and this is a strong philosophical concept. Yes, so if you attach environment, somehow interact with it and detach environment, then you can go from poor state to mixed state. And this is the typical way how noise appears. So noise appears if you interact with external environment. And you interact with that means that you have a certain joint state with B, yes, between A and B, and after this B goes away, so you stop to interact with it, yes? This is how the noise appears. Yes, okay. More complicated system. Yes, so now I just immediately wrote the state AB, and what would be its partial trace? What would be its density operator? Let us do the following, yes? Let us more concentrate on the first example, and might be you will ask as many questions as you want, as you can to the first example in the beginning. So when I calculated partial trace of rho AB, was it clear how I did this?
I got a little bit confused in in the middle rectangle. There is trace of psi and psi, and I got lost.
So there is a trace of psi, yes, and because we know that psi is a sum of 0, 0, 0, 0 plus 0, 0, 1, 1 plus 1, 1, 0, 0, 1, 1, 1, 1, yes. So because we open, yes, we just open those brackets. Yes, just formally open those brackets. And we know that partial trace is a linear operation. So the linearity of the operation, yes, means that in particular, yes, so that if you consider rho 1 plus rho 2, yes, it is equal to trace of rho 1 plus trace of rho 2. Yes, so that this is a linear operation of them. Yes. So this sorry. So this means that we can represent it in such form. Yes, so this is now sum of 4 trace operators of a simpler form. And I'm so happy because now if I look onto this state, yes, 0, 0 times 0, 0, and I look on the previous slide, yes, I look on the definition of the partial trace, yes, I see that the state 0, 0, 0, 1 satisfy assumptions of the second line. Yes, so this one. Because this is just a direct product. This is a tensor product here. So this, each 0, 0 is tensor product of 0 and 0. Here it is also a tensor product. Yeah, so then it is just equal to the tensor product of first 0, 0 plus tensor product. So I can write here, not 1 and 2, but maybe A and B. Yes. So this is a tensor product of such guys. Yeah, so it's might be this is a bit confusing step. Yes, and after this I can apply the formula from the density operator. So I put here the first term, so previous A. Yes, and here is B. Yes, so the partial trace of the cell. Yes, and so scalar product of vector with itself 0 is 1, so it is just equal to 0, 0. Is it still confusing?
No, that part I got it, but in the next rectangle, that you write the partial trace of psi and psi is equal to 1/2 of, I think, it's psi times psi plus 0. That 0 I didn't got it.
Oh, you mean this one?
Yes, in the middle.
Yes, because you see, so I have here the second term, partial trace of 0, 0, 0, 0, 1, 1. And I got it that calculate, I got the product of 0 times 1, outer product, times a number. And this number is happened to be 0. Yeah, so, and then it is a 0 vector. Yeah, so this is 0, a number, and this is 0 vector. Yes, it's quite confusing because here 0 can be a vector, 0 can be a number, and 0 can be 0 vector. Yes, so let me rewrite it here. Yes, I will write here 1/2 times 0 times 0, 1. Yes. This is the second term. Yes. Plus 1/2 times 0 times 1, 0. Here it is. 1, 0. And plus 1/2, 1, 1. Yes, so here it is 0 times 0, 1.
Okay.
Yes, so this is a certain formalism. Yes, and in the end, I got a matrix 1/2, 0, 0, 1/2, which corresponds to this state. Yes, so with some probability, with probability 1/2 you are 0, and with probability 1/2 you are 1. Okay, yes. Try to ask more questions because I have a feeling that it is quite confusing, and that it is, yes, because I was not a good guy and not able to give a good definition, yes, of the partial trace, so I was only able to write it as a certain formal way. So it is linear, it is defined somewhere, yes. And then let us try. So before we try the second one, let us finish with the first one. Okay, let's come to the second one. Then, so now I erase everything here. And write the second. So here the numbers are just chosen, so to be different, don't look any meaning of them, yes, of diagonal elements. Yes, and they're chosen small just to be sure that this is a density operator, because it should be positively defined. Yes, but now there is a problem that we have a lot of non-zero elements here. Yes, and I will write here like this: 0, 1, 1, 0, 1, 1, 0, 0, 0. Sorry. It's better to write in other way. 0, 0, 0, 1, 1, 1, 0, 1, 1. Yes, and now, yes, I will start to do the following. So this is my role. Yes, this is my role. And I would look, I mean, this is the most straightforward way to do it. Yes. I will write the trace. I will look on each number here, yes, and will look what is its trace, yes, to what it corresponds, yes. So this would be equal, yes, to trace B of 0.25, 0, 0, 0, 0, yes, plus, yes, and let me now on the back side, yes, do this calculation. Trace B of 0.25, 0, 0, 0, 0, 0. Might be you can say me what it would be. Yes, we put 0.25 on front. We looked on the first elements here. We just copy them. And for the other two, we look to their scalar product. Yes, which is 0.25, 0, 0, 0, 0. So I replace here, I erase here like this, and write 0.25, 0, 0, 0, 0. And okay, I already made this one. Yes, I already made this one. Yes, so I would just do term by term. Okay, this guy, it will give me 0. Yes. I will write it in a form also 0, 0, 0. I mean, just because here 0 was a front coefficient. Yes. Now, let me look on the next term. Yes, on this one. Yes. So I need to calculate trace B of 0.01 of 0, 0, 1, 0. Yes. It will give me, first, I put 1 over 100 in front. The second, I consider those elements, so I got 0, 1. And the last, I can see the scalar product of those two. So times 0, 0 is equal to 0, 0, 1, 0, 1. And so the next term would be plus 1, 0, 1, 0, 1. So interesting is the next term. Let me look on this one, because this would give a slightly unexpected result. Yes? So I write trace B of 0.02, 0, 0 times 1, 1. Yes? Actually, we have seen this already, yes, on the previous part. Yes, it will give me trace B, it will give me 0.02. I consider the first elements here, and multiply on a scalar product of 1 and 0. And this is 0. So it's equal to 0 times 0, 1. Yes, so it is, oops, it is equal 0 times 0, 1. And I finish, so in the end, what we see, that this guy gave us no impact, this guy gave us impact, and this guy gave us impact. What was common between them? The common was that the second term here, coincide. And in the places where they were different, it just disappeared by this rule. It might look a bit confusing. Yes, it might look a bit confusing, and it comes only with practice. Yes, so this is why we do this here. So the next term, yes, so the next line, it would be 0 times 0, 0. Yes, here it is coincide, so it would be plus 0.25, 0, 0. And let me pay attention. You see, this term and this term gave the same output. Yes, so they would summate in the end. Yes, so next one, 0, which gives us 0, 1, and the last one would participate because here 1 and 1. Yes, so we would have 0.03, 0, 1. Yes, and okay, the next thing is 0.01. 1, 0, plus 0 times 1, 0, plus those two coincide. So this is plus 0.25, 1, 1. And I mean, I guess it becomes a bit boring. Yes, but let me finish. Yes, so this one gives me 0 impact. Yes, 0. This one gives me not 0 impact. 0, 3, 1, 0, 1, 0. This one gives me 0 impact. Yes. And here there are a lot of terms. Yes, but all of them are one-coded. So there are just 4 different products. Yes, and let me just use one more color and just highlight. We have here 0, 0, 0, 0, 0, 0, and there should be 4th 0, 0. Yes, those two. We summate them and we get the last line. Hope you can see it. Yes, so we will have 1/2 0, 0. Similarly, we will get 1/2 1, 1. Yes, but we would get something non-trivial on 0, 1. Yes, and let me. Yes, so here 0, 1, 0, 1, 0, 1, and 0, 1. Yes, it would be some value for 0, 1. And I mean, I did this calculation before, it would be the last term would be 1, 0 as well. So the total matrix would be 1/2, 1/2, 0.04, 0.04. So those two guys play a role. Yes. And those guys didn't. Yes. And so this is a kind of when we make a detach of the system, you should think about partial traces that you remove, that you A and B separate. Part of the matrix becomes not important. Yes, so that's kind of you lose. So this was an entanglement between A and B, and you lose it. This is what happened partially. Yes. And yeah, I don't know what to say as a philosophical concept. Yes, so in the end, you get certain state of system A. Important here is not the result. Important that we can do this. Yes, the goal was just to demonstrate that definition from the previous slide is enough to be a definition. Questions?
So like that, the first density matrix that you gave would be a mixed state that there is the environment in there.
Here. It is a mixed state of a 2-qubit system. Yes. It's not a pure state. It's a mixed state.
And in this mixed state is the environment already.
Yes. So kind of you already you are together with environment and you are in a mixed state. Yes. So kind of the most complicated situation which could be. Yes. Good point.
Okay.
Good point. Yes. Thank you. Yes. So this is quite a simple case, yes, and this is quite a complex case, yes, and I especially use the matrix with random numbers, let's say, yes, just to show that whatever it is, you can just calculate element by element, each element of the matrix becomes one term in this sum, yes. And this job is quite heavy, yes, but in fact, if you work with noise, this is more or less of what you more or less have to do, yes, because it's so there is list of jobs, yes, now available on the market for quantum computing. This is jobs from companies which develop quantum computers, so they build physical devices. And they want to know what errors do they have. Yes? So in fact, you never know, what is your current density operator. You can only measure and get results. And they do some operations on a quantum computer, and they do a lot of measurements, and see their results, and they try to understand what are the errors which appears in those computers. Yes, and in that case, okay, of course on Python, but not by hands. Yes, but you have Python or other language. Yes, you have to operate basically with those matrices. You try to feed the best which noise would give you this results. You can do this with on a 1 qubit level, you can do this on multi-qubit level, and so on. So this is real vacancies, yes, which exist. So because of this, if you're going to this work, yes, it's unavoidable for you to ignore the existence of density operators and how the traces looks like. This is why I have to, and in the end, there would be no algorithm in which I would use density operators as it is. Yes, I would show one error correction code, yes, so how you can reduce errors. Yes, the motivation there would be the fact that all operations are linear in a language of density operators. Yes, so this will be an important part. But still, exact calculations could be needed only if you go to, I don't know, to hardware. Yes, but still, I hope that the course would prepare you to real work, and such type of work exists. More questions?
Another thing that I can't see if, like, doing this partial trace, it reduces the error or stays the same?
No, it loses some information. This is the next in the next slides we will see how technically it's happening. Yes, but you should think as the following. So your system A, you were staying here peacefully and quietly. Yes. After this, some environment comes to you, attaches to you somehow, and disappears. Yes, it would took from you some certainty. Yes, and I didn't say here how you created this row AB, because originally you were just a good state row A. Yes, I don't know what it was. Yes, after this appears B, it attaches to you. It somehow did something with you and detaches. And this is what is happening. And at that moment, it happens a lot of information. So you kind of have less knowledge than you had before. You should think about this like this. Okay, so I suggest to have 5 minutes break and continue. So, what for partial trace is needed to determine what is happening with the noise? So let us consider the following. So this is okay. Sorry. Before I go to the explanation how it affects the noise, there is important more statement. It's called purification. Consider arbitrary state. It is a mixed state of system. Yes, the statement is the following. Then there exists an extended, you can extend your system. Potentially there is a certain another set of qubits and certain poor state psi of this extended system, such that if you consider partial trace of this extended system, that you get a mixed state. So this is demonstrate the idea, yes, as was shown in first example, that whatever mixed state you have a poor state of a bigger system, such that your mixed state is just a partial trace of it. Yes, and mathematically the proof is not difficult, so because we already have seen that any any density operator can be represented in such form, so sum of probabilities poor states, but in such way that those poor states are pairwise orthogonal. Yes, and then it happens that we can say, we can take R as a copy of A and just a state which would be consist of elements the square root of pk, and we would have two copies of vector psi k independently. This is very well fits to what I showed in example 1. In example 1, that was showed the partial trace of one of psi, where psi was 1 over square root of 2 z plus 1, 1. Yes, that this would be equal to the density operator 1/2 to 1/2 0, 0, which is P0 the state 0 is P0 equal to 1/2 0 and P0 equal to 1, P1 equal to 1/2 state 1. Yes, so this exactly corresponds to this story. Yes, if you consider reverse engineering. So this is the mixed state, and you consider a poor state which would consist of 0, 0, 1, 1, with the coefficient 1 over square root of 2, square root of probabilities. Yes, so I would not prove, yes, that the partial trace of this guy would be equal exactly to that one, but it is true. Yes. So what typical operations are happening? Yes. So if you have your quantum computer and you want to make an action with it, what you do? Somehow appears environment. So you go in a state rho, and you becomes appears environment. So it is also density operator corresponding to environment, and they are independent. So they have tensor product state. After this, you do some operation over there. Yes. So you consider some operation of this form. Yes, and because this is a quantum mechanics, and we are allowed only to have unitary operations acting on the system. Yes, so you do like this. And know that, okay, it was a direct product state. Potentially, after applying operator U, it's not a direct product state. And after this, you detach environment and you remove it back. Yes, and this is how typically works. You have a system, you put something closer to it, you do something together, you remove environment back. This is how, I mean, everywhere it works. Yes, and in that case, detaching environment is the same as taking partial phase phonetically. Yes, so this is physical action detaching environment, removing it far, yes, is the same as taking partial phase. Yes, and in that case, all the operations which we able to do have those forms. So now, yes, what is happening, the difference? Before we had a system, yes, it was psi, and we applied to it unitary operators. Yes, and it goes, psi goes to u psi. And now we say that we slightly extend our possibilities. We say, no. We can also, for some time, add some more qubits to the system, do something together, and remove those qubits back. And this can happen with your will, yes, so that you wanted to do this. And in that case, you typically can just apply U to A. Yes, you kind of will do this in a way such that it would not disturb the independence of A. But sometimes it happens not because you want, but because it just happened. You know, some photon was flying around, some temperature fluctuation has happened. Yes, and then it happens that you interact with kind of, you consider your system bigger, so with this photon or I don't know, something else happening around, it happens some operation. It is from quantum mechanics, and after this, this environment disappears. And this is what potentially you can do. And let's not do example, yes? And then what has happened, yes? You have these operations. This is now a larger list of operations which we can do. And this is really new operations which didn't exist in the world of pure states, but they exist in the world of mixed states. So really the quantum mechanics give you a larger set of possible operations for mixed states. Yes, and here you have two parameters, unitary operator U and rho environment which you attach to the system. Yes, and it happens that it is not the best way of making parameters here. There is a better way that you consider. So for any such operations, U and for raw environment and U, there is a pair of linear operators ek, yes, such that some of their ek, like its conjugacy applied to it, the sum of such matrix is identity, such that the whole operation, so this operation looks like what is written here. This is a mathematical statement I omitted, yes? But this is called operator sum representation, and this is now considered as a new world of all possible operations which we can make. So now we can make all operations from now on, yes, which are represented in this form. And this is a restriction of quantum mechanics. Yes. So formally, I am able, to omit the notion of partial trace, yes, and say that, okay, as soon as we come to mixed states, this is a new world of operators which I allow. Yes, operations which I allow, which could happen. It's not that we want to make them, but this is the operations which happens. And so the property, the second term, yes, so this one, is good and it is necessary because as soon as it is satisfied, then actually such a sum would be necessary also density operator. So it will also be self-adjoint, positively defined, and have trace one. Yes, so this is a consequence of this fact. Yes, so this is new type of operations. And all previous operations which we saw is a partial case of those ones. Yes, so applying of a unitary gate, yes, it was, we know that on density operators, it acts as a conjugacy. In that case, it corresponds to the family of operators. Ek is just one operator. This is operator Q, yes, because it's unitary. Some of the product is its conjugacy. So it is identity, yes, so this is satisfied. And now the sum disappears because we have only one element. So it becomes like this. The second thing, it happens that if we can see the measurement with respect to family of spaces, and this is bad notation because this Ek is not equal to this Ek, yes? But then we could consider list of projections on those spaces and consider that in that case, some of the projections conjugated, applied to them would be an identity operator. Yes, and then we know that the measurement acts like this. Yes, so once again, it becomes an operation of this type. So as soon as we now postulate that those operations are allowed, we immediately come to the world in which all previous operations are allowed as well. So this is the world of these operations is larger than the world of operations which we considered before. But another example, unfortunately, is not operations which usually happen by our view. It would be quantum noise. It's something which happens because it happens. Yes. And questions? So now I introduced new form of how I act on a quantum state. And this is much more complex and much less intuitive. Yes, but this is the physics. This is also a consequence of quantum mechanics. In fact, I showed certain ideas how it is happening. Now let's come to noise. And this would be more a descriptive story. So I would not give a certain motivation, I would not give calculations. I would just say the world is constructed in such a way that quite often happens exactly those operations. So that the noise usually comes in such form. Yes, so first operation is bit flip. Yes, remember this is the form which we could have. And I formally postulated E0 is square root of P of some of identity, and the E1 is 1 square root of 1 minus P of not operator. And this has an interpretation that with probability P, nothing has happened, no noise, and with probability 1 minus P, we change between 0 and 1. Yes, so 0 becomes 1, 1 becomes 0. This is called bit flip. Yes, so with probability 1 minus P, you make a mistake in a system, and mistake of a specific form X, of not operation. Yes? And so if you had a poor system with the state A0 plus B1, yes, then with probability P, new state will be A0 plus B1, and with probability 1 minus P, it would be the state B0 A1. Yes, so kind of the basis vector space. So this is what happened. Yes. And we can make a calculation density operators. Yes, so I can see that this interpretation, or it, like if you calculate it carefully, it would be equal to what is written here. Yes, so that's in this form. So the informal interpretation and formal, they coincide. And the vectors are here. Yes, the matrix. I don't see a big reason why we need to analyze exactly how matrix will look like. The idea that we can write in such form, or the noise of the type that bit is changed into opposite. Yes. But why we change the why we change 0 and 1? Why we apply operator X? Why we not apply another operator? Yes. And you can do the same with probability P. You don't do anything. With probability 1 minus P, you change the phase. So you apply the gate Z. And then you have those operations. Why not apply the gate Y of this form, another Pauli gate head? And by the way, it happens that Y is related to X and Z. So this, because it's quite often called bit phase flip. Yes, so that's it changed both bit phase. Yes, so that's a descriptive version. And this is typical story. So we had these basic gates X, Y, and Z, and kind of we say that this probability P we do nothing, and this probability 1 minus P we do one of them. Yes. Interesting thing is a so-called depolarization channel. And I list those things because they just quite often appear. So let us do the following. Probability P, it stays as it was, and with probability 1 minus P, we completely loses the information. So we become in a state with probability 1/2 we are 0, with probability 1/2 we are 1. This is kind of analog of zero information. Yes, okay. That's all the results of our calculations are lost. Yes, and then you can say that, okay, formally the image of the state rho would be 1 minus pi, half of identity. Yes, so to this corresponds half of identity plus p rho. Yes, and you can see that this is not in the form like this. Yes, so one can say that no, okay, this is not possible. Not possible to have a complete law of information. But the life is more difficult. Yes, in fact, we have an identity. Yes, that if we consider half of sum of rho x, y rho y, and z rho z, then we will get identity. We saw this when we considered Bloch-Ball definition, but I would like to recall that it's necessary that you have some identity of this form because, yes, the general form of density operator is the following. So you have on diagonal values A and 1 minus A because the trace is equal to 1. And on off-diagonal elements, you have complex conjugated values. So C plus ID and C minus ID. So this is a 3-parameter family. So if you consider 4 different values, rho x, y, rho y, and z rho z, there would be some identity which connects them. So they cannot be completely independent. Yes, and this identity, it happens this one, and if now you substitute instead of identity this expression, you will get something which has the form of operator sum representation. Yes, so this is also a possible operation. And the last one which I would like to show is so-called amplitude damping. The reason why it's called amplitude damping has a physical reason, so it corresponds to certain photon appearing, and it comes to physics. Usually, if you have a qubit, it is either in state 0 or in state 1. And they usually offer different energy level states. And in that case, quite often it is of different energy level states. And in that case, there is a higher probability then you move from high energy state to low energy state, so then to other direction. Yes, and in that case appears a property that, okay, with probability, with a small probability, that state 1 goes to state 0. And this would correspond to such matrices as 0 and E1, which are not, now they are not diagonal, and they are not symmetric. Yes, so note that E1 is not necessarily self-adjoint, yes, but it still would satisfy this identity. Okay, it's, I mean, have quite a long list and quite heavy notation. Yes. So, and now I would like to say why noise is so horrible. Why there is no way that you really kind of well adapt to a noise in the system. So why you have to fight with it. Yes. And for this, I need notion of distance between quantum states. And for poor states, yes, it's quite an easy story because we know that they're vectors in a Euclidean space, so why not make just the distance between them? Yes, and I informally used it in Grover's algorithm, for example. Yes, and but I want to have this for mixed states. And to mixed states, okay, for one dimension, for one qubit states, we have a notion of block ball, but for multi-qubit states, we don't have a good representation instead of matrices, yes? And what means that the matrices are closed, we need to define, yes? And the second thing, I'd like to explain why noise is bad. And in a distance which I would introduce, it would happen that every noise which is happening make the distance between states smaller. So kind of if you consider very, very long circuit, and from whatever initial data you start, you would end up with the same. And this tells that basically you calculate nothing. Yes, because it was independent of the initial state. So I mean, this is a predefined failure. This doesn't give you computational power. So this is a bad part. This is a bad story, dark story of that one. And for this, so there are several notions. The easiest mathematically is the so-called trace distance. And it's called that if we have two states which are represented as a density operator, then we can see the distance between them is 1/2, and why 1/2 I will show later. Trace of the so-called absolute, so modulus of the rho minus sigma. And the modulus of matrix is square root of its product with its conjugacy. Yes, and note that here rho minus sigma is self-adjoint, so A star is equal to A, but still it's not true that square root of A squared is equal to A. Yes, we remember that square root of x squared is absolute value of x. Yes, and here it is the same. Yes, so let us do some calculations. Yes. For example, consider matrix 1/2, 1/2 on diagonal and sigma just 1, 0, 0. So this corresponds to 1/2 probability of 0, 1/2 probability of 1, and this corresponds just to have the value 1. Yes, rho minus sigma is minus 1/2, 1/2. If you consider it squared, yes, you will get that. So A is equal to rho minus sigma, then A star A would equal to 1 over 4, 0, 0, 1 over 4. Yes, because minus 1/2 is squared. Yes, and then when you consider the square root of it, you will get positive 1/2. Yes, so that's you kind of just take you can put input on the eigenvalue basically. And this is exactly what is happening. And then the trace of this is 1 and the distance is 1/2. Yes. The second example. Yes, now it happened that you have rho is still probability 1/2 0 and 1 independently, and here this is sigma corresponds to poor state 1/2 1 over square root of 2, 0 plus 1. And Then if you consider the difference, yes, it would be 0, 1/2, 1/2. 0, you multiply it onto itself, yes, and you will get still the same matrix as in the previous time. Yes, yes, yes. And then you will get the same distance. Let me not do more examples. Let us make it. Let me hold. Yes, and then as one of the properties which allows to prove the statement is the distance between two states is the maximum of the trace of the projection of rho minus sigma. So I put maximum of a projection, so you put just projection here. So usually it is part of it is positive, part of it is negative, kind of just with a projection you can remove the negative trace part. And the trace becomes metric. So it is bigger or equal than 0, it is equal than 0 only if rho and sigma coincide, and it satisfies the triangle inequality. This is what we enjoy. What is nice, so for one cubic state, it coincides with the Euclidean distance. So for every state, rho and sigma, we had a point inside the Bloch sphere. So then it happens that the trace distance is exactly the distance between those 2 points in an Euclidean sphere. Two important things. Yeah, so when you apply unitary operator, then you do not change the trace distance. I do not prove this property, but it is true. So when you do classical calculations, yes, in the form which we did before, you don't kind of make the results closer, so you keep the information. And another thing that if you have operator which is in the form of operator some representation, then the distance between any two states cannot become, so it's not rho, it should be E of rho and E of sigma here. Then the distance between them cannot increase. It only can become smaller. And this corresponds to the notion loss of information in that system. Yes, so any operation in the contraction, you not necessarily have here strict inequality. You can sometimes, it can stay the same as it was before, but it cannot increase. So if we have noise in our system, then if it takes long enough, then everything would be washed out, basically. So everything which would happen would goes to the state, to the same answer. Yes, so it's much reduced calculation power. And in physics, people more use another distance fidelity, but I'm looking on the time and I think I will skip it. And also there is a topic of error correction, which I also think I will give on Tuesday. Yes, and the next lecture is the last lecture. Yes, and after it I will give a list of questions. And we need to coordinate the date of exam. I suggest it for those who want to pass. I suggest to put it on the first week after the carnival. But okay, let me stop recording.